In this video, we'll look what happens to the charge, voltage, energy, and electric field of a capacitor before and after you put a dielectric in. So once again, we'll start with our before and our after picture. So initially, we'll have a capacitor, an air-filled capacitor. The distance between the plates will not change. We'll charge it up. And so we'll call all the initial values: initial charge, Q0, initial capacitance, C0, initial voltage, V0, initial electric field, E0, and initial potential energy that is stored in that electric field, PE0. Okay, so those will be all the initial quantities. The governing equations, that capacitance is Q over V naught. The electric field between the plates is the voltage over the distance between the plates. And the potential energy, we have two formulae we can use. One half C0 V0 squared, or if it's more convenient, depends on what we know, we could use 1/2 Q0 V0, and those are actually the same formula. Okay, so now we come along and we put a dielectric in, and we want to know what happens to all those quantities. Okay, so here's the dielectric material between the plates. The dielectric will have a dielectric constant of kappa, and kappa by definition is greater than 1. Okay, and that's a property of the material that you put in, maybe mylar, paper, or could even be water or something. Now they'll still be charged here. Okay, so now what happens to all these quantities? Well, right off the bat, by definition, the capacitance of this capacitor goes up by a factor kappa. So now all these quantities without the 0 are going to be the final value. So final capacitance, so this increases. And that's because the electric field decreases because of the polarization of the molecules in that dielectric constant. They tend to oppose the E0, the original electric field, therefore decreasing electric field, which then decreases voltage. Now, the final charge on this capacitor, it can't change. It remains Q0. There's nowhere for it to go. There's no battery. It doesn't jump it through the gap. And so that stays constant. And that's because there is no battery and nowhere for that charge to go. Okay, once we have C and Q, that dictates the voltage. The voltage by definition is Q over C, and this new charge is the same as Q0, but the new capacitance is kappa C0. And so this voltage is related to the initial voltage by a factor of 1 over kappa. So this goes down, this decreases, as I said, because of that electric field decreasing. Okay. The electric field, which is defined to be the voltage per distance. Distance isn't changing. We're not spreading the plates or anything. So this will now be V0 over kappa D. And so this is E0 over kappa. And there's that decreasing electric field because of that dielectric. Now the potential energy stored, which is half QV, will be 1/2 Q0 V0 over kappa. And so this will be the initial potential energy divided by kappa. So this has decreased. Now where'd that energy go? Decreases. Well, what actually happens is when you start bringing this piece of dielectric material close to these plates, so this is plus, 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 minus, minus, minus. And you start introducing this dielectric material like this, you will distort the field. So what will happen is the top of this dielectric will become negatively charged, the bottom will become positively charged, and the electric field lines, which normally go like this, between this parallel plate capacitor, start to kind of pull over like this. And they kind of get distorted like this. And this distortion of these electric field lines creates a force. and that actually sucks this dielectric in. So these components of the electric field like this, that kind of go like this. There's now a tangential component, and this gets sucked in. That's where the energy goes. It uses it to suck in the dielectric. Now, if this were connected to a battery, it would be a different situation. So if it's connected to a battery, remember, a battery is a source or a sink of electric charge. And so there is somewhere for charge to go. So if we keep the battery on this capacitor, when we put the dielectric in, now it's got the dielectric over here, that still has the same battery. So if this is V0, this is V0, this is V0. The voltage cannot change if you're connected to a battery. Now, capacitance still, this is still C0. This capacitance will change. This becomes kappa C0. So the capacitance still goes up when you put that capacitor in. But now the charge, because this voltage has stayed the same, the charge, which is CV, this final charge, that's the same as CV0 because the voltage stays the same. And so this is now kappa C0V0. It's kappa Q0. There's more charge, so this increases. More charge goes on to capacitor, and that charge comes from the battery. And this would be a situation where you would take charge off that battery and put it onto that capacitor. Now the electric field, defined to be V0 over D, this would stay the same. Okay, now I just said that when you put a dielectric in, the electric field goes down, but if you put more charge onto the capacitor, that's compensated for by that electric field going down. So in fact, the electric field stays constant. Okay, you've got more charge, and so that compensates for the electric field decreasing because of the electric field in the dielectric. Now the potential energy after this dielectric is in there actually goes up by a factor of kappa. This new electric field is kappa P0. So it's increased potential energy. Where did the energy come from? Well, it came from the battery. It's because the battery put charge onto that capacitor, it's supplying energy. Okay, so this energy increases. So you can see that's a totally different situation than when you don't have a battery connected and you put a dielectric in. Okay, so that'll do it.